Hello, welcome everyone. Good morning. We are going to go ahead and get started with the presentation from the PRC Director, Dr. Swami.
Thanks, Sherry. Good morning, good afternoon, good evening to all of you. There are people joining today's tutorial from all around the globe. We have more than around 250 registered, so I'm sure they'll continue to join. My name is Madhavan Swaminathan. I'm with Georgia Tech, with a couple of schools that are shown here, as well as the Packaging Research Center. And the title of today's tutorial is Demystifying Machine Learning for Packaging Problems. So I've included semiconductor here just to make sure that whatever I'm going to be talking about is related to semiconductor packaging. So with that, let's get started. So my suggestion is that you please mute your microphone and post your questions in the chat box as and when you want to ask questions, and I'll try to answer them as much as I can. And assuming I'm not able to answer them during this tutorial, I'll try to provide answers to these later on. I'll break the presentation as follows: 40 minutes for the first part with 5 minutes for Q&A. And the second part will last for 40 minutes with another 5 minutes for Q&A. And basically this tutorial is for an hour and a half. And this will be recorded. Unfortunately, we cannot share the slides with you, but we can share the recording with you. So before I continue, I want to recognize a center that we have here in the United States called the Center for Advanced Electronics through Machine Learning. So a lot of the work that I'm going to show today is a result of the work through the center, which is a collaborative center between University of Illinois Urbana-Champaign, NC State University, and Georgia Tech. And this is supported through the National Science Foundation. So if you want to get more information about the center, please go to this website. There's a lot of information on some of the projects that we are working on. So today's tutorial is going to be based on a paper that we published recently with a title very similar to the title of the presentation. So if you're able to download this paper from IEEE Explore, that would be great. Otherwise, if you're unable to access IEEE Explore, please send me an email and I can provide you with this paper. So the target audience today is threefold. One is the non-ML engineers wanting to learn about machine learning and its applications in packaging. So that is where this term demystifying comes in. I also want this to be a motivational tutorial for researchers working in this area. These are students, faculty, researchers working in companies, and so on and so forth. And number three, experts who want to understand the problem that needs to be solved and possible methods for solving them. So once again, this machine learning area is a very vast area. It's impossible for me to cover every aspect of machine learning today. But what I'm going to do is to put this in the context of packaging, specifically on design, under the hope that some of these concepts that I'm going to share with you can be applied to other areas as well. So let me start with what is machine learning. So I'm sure all of us are familiar with data mining. Those in the computer science area have been working in this area for many years. And here you try to extract insights from data, and you make use of several techniques such as statistical methods, data analytics. Machine learning was one example of the technique that you can use. So I call this data mining as a superset of machine learning. Now, there's also been a lot of work done in the area of statistical learning. And here what you do is you have data or data samples, and you fit some theoretical distributions to data. And for example, you say that the data is a normal distribution. So you fit a normal distribution to it. And because of that, it meets certain assumptions. And therefore, you can mathematically prove the results that you can obtain from this kind of a distribution, and you can derive inferences from it. Now, if you look at machine learning, you rely on computers to probe the data for structure. So the way you develop this model is by validating error on new data, what we call as the test data. So there is no theoretical test that guarantees that whatever model that you have developed indeed is accurate. So you rely on this error control as a way to manage the results that you get from data. However, we have very powerful computers today and very cheap memory. And as a result of that, machine learning approach becomes very, very compelling, because you can work with large amounts of data, learn the patterns from this data, and come up with inferences based on that. So as an example, if you're looking at deep learning, it looks at complicated patterns and large amounts of data to be able to determine features and things like that you can try to recognize. So let me put this in the context of packaging, specifically design. And I call this as the model-based design paradigm. Now, typically when we do in design, it doesn't matter if it is packaging or let us say it is in the general area of semiconductors, you have a design space and a set of design goals. And you rely on ways by which you can generate data in this design space such that you can look at various variations of the design to make sure that it meets the goals that you're interested in. And oftentimes we rely on simulators. And these simulators could be SPICE, it could be some kind of a TCAD, designed for manufacturing simulators, electromagnetic simulators, physics-based, it really doesn't matter. You rely on these simulators to generate data. And oftentimes what happens is that when you generate this data and try to do this designs, it tends to be a very, very slow process. So the whole idea is to somehow speed this up. And that is where you try to replace these slow methods for model generation through these fast models. And the idea here is if you can create a machine learning environment that replaces the typical way by which we do things, then you rely on these models that you have generated using this machine learning kind of an environment to do all of your design as well as, let's say, your optimization. Please realize that this machine learning model that you're trying to develop, you're relying on data from the original slow simulators so that you can learn how these data samples actually behave and rely on that to be able to create these fast models. So the whole idea here is you want to use these fast to evaluate learn model to replace the slow models in design and design optimization. And today I'm going to try and cover two elements of this. One is how do you build these fast models? And the second is how do you do design optimization? Okay. So let's start with the fundamentals of machine learning. So let us say that you're working with a one-dimensional problem. So you have one input and let's say one output, and they are somehow related to each other through a function f that is unknown. So what you try to do is you try to gather data, and you gather these data as shown over here. So for every input x1 to xn, you have a certain output y1 to yn. You group this data and you call this as the training data. So these are the samples that you have generated. You use this training data to go through this machine learning kind of an environment to come up with a learned model. What this basically means is that creating a relationship between the input x and the output y. That's what we call as the mapping. But the mapping that you create is through some kind of a function h, which is not the same as the function f. So as a result of that, you will always have some level of error because these two functions do not match. But the idea is to reduce that error as much as possible. Once you have done that, you rely on the function h in such a way that for any arbitrary input, x1 to xn prime, you are able to get the output y1 prime to yn prime. And notice that this is new data. It is not the same as what you used for training. So therefore, if you look at machine learning, there is one part that relies on training and another part that relies on prediction. Now, if you look at this problem, it looks too simple. You say all you're trying to do is to create a mapping between the two. What is the big deal? So let us try to expand this problem to very real situations. Let's say that the dimensionality is much, much greater than 1. So let us say it is around 50. Let's say that this relationship is highly nonlinear. Let's assume that the output response is unknown. You just don't know what the output is. The data range itself is very large, and the samples that you're trying to generate are expensive to begin with. Basically, the samples that you're using for training. Under such scenarios, the machine learning based methods can provide significant advantages. So let's look at the limits and needs for packaging problems. So in this tutorial, as I mentioned earlier, I'm going to break it up into two parts. The first part is trying to give you some flavor as to how to make use of these artificial neural networks. I'll look at three that are, I think, important for packaging problems: a feed-forward neural network, a recurrent neural network, and convolutional neural network. And then the second part is going to be on Bayesian learning, where the benefits are optimization. You can do fast model generation and so on and so forth, and try to take you through three aspects of this learning solution that is indicated over here. Now, for all of these, I'll try to pose some problems and show how you can solve these kinds of problems that tend to be quite complicated. And finally, very briefly, I'll touch on some future directions in the area of dimensionality reduction, extrapolation, and invertible neural networks. So let's dive deep into it. So let us see how you would create a neural network. So if you look at any neural network, the fundamental building block is a neuron, right? We also call this as a perceptron. Now, if you look at this perceptron, it has some inputs associated with it and an output. Now, if you look at these inputs over here, W represents the weights and X could be some input coming in. So you're weighting the inputs that are coming in through these values W that are shown over here. Then you add them all up. That's what is shown here as the summation. Then you add a bias to it. And the way you figure out what a bias is if you look at any kind of a curve fitting, right? Let's say it's for a single input output problem, you have some kind of a line that describes the relationship. And let's say you plot it and that line has an intercept associated with it. That intercept is what we call as the bias. So we add a bias to it and realize that so far everything that I've shown represents a linear operation. But if you're looking at nonlinear kinds of responses, you have to bring nonlinearity into the solution as well. And that is where this activation function comes in. So the activation function, along with providing nonlinearity, it also allows you to bound the data. So it limits the range of the data that you're making use of. And at the output over here, you have some kind of a response that is defined over here. So we take the single neuron and start connecting them to each other. and we create these layers. So in each layer, you have several neurons, and you have many such layers that you put together. And you create this connectivity, essentially a network, in terms of how these neurons are connected to each other, and how the input is connected to these neurons, and how these neurons are connected to the output. So if you notice here, every neuron is connected to every other neuron, and this is what we call as a fully connected neural network. The other thing you will notice is that all of the arrows here point towards the right-hand side. So we call this as a feed-forward neural network. Now, you have to somehow reduce the error, and that is where these back arrows come in. So this is the way we control the error between what you are able to generate here at the output and what the exact output needs to be. So there are algorithms available that allows you to control the error by adjusting these weights that are shown over here. So the key takeaway here is ultimately the data patterns determine the neural network architecture we want to use. And in this example, the feed-forward neural network is an example of a neural network architecture. So how would you build a neural network? So the first thing is you have to define the problem, right? In terms of what are the inputs and what are the outputs. The second part is the domain expertise. This is extremely critical because you have to be an expert in the problem area to try and understand what kind of a functional relationship that you're trying to create, and also identifying data structures. So for example, how important is the memory? I'll address this later on, spatial correlations and things like that. And then you go through this neural network design process. So you determine what kind of a neural network you want to make use of based on information that you have about the problem you're trying to solve. And then you design your neural network architecture that determines how many layers you need, how many neurons you need, and things like that. Then you have to generate data. There are various methods available to generate data. We call these as sampling strategies. One example is called latent hypercube sampling. It's used quite a bit in the machine learning community. I provided a Wikipedia link over here. It's just a way by which you can create your samples. And then you use this to train the neural network by defining some kind of a loss function. We call this as an error function. And once you've been able to minimize the error, you've just created a model that you can make use of to make your predictions. So let me start with problem number one. So this is an example of an antenna. So once again, problem itself is not important. I want you to sort of really appreciate why this neural network kinds of approaches are very useful. So let us say that I have some kind of a material here, and these blue circles represent metal particles, like for example, nickel or cobalt, and I'm somehow coating it, right? That's the white region that is shown over here called an oxide. And then I'm putting it in some kind of a polymer. So I'm creating a nanocomposite material. Now, based on how you do the mixing and what material you choose, there are a set of complex equations that determines what kind of a permeability and permittivity you're going to get from it. And that essentially will tell you how this permeability and permittivity would behave as a function of frequency. Then I make use of this information to, let's say, design an antenna. This is an example of a planar antenna. And then I optimize this design over here such that I'm able to reach my objectives such as the gain, radiation efficiency, bandwidth, resonant frequency, and so on and so forth. So this is the process that you need to go through. Now, what we can do is basically hide all of those intermediate steps through a neural network so that somebody who's developing these nanocomposite materials can determine what kind of properties you need over here to be able to get the kinds of objectives that an antenna engineer would like to get, right? So this becomes a very, very powerful technique because you can now go all the way from the materials aspects of the problem to an end solution. And that is what is indicated over here. So there are two parameters that has been made use of here. One is the radius of the particle, and the second is what we call as the volume fraction. They become the inputs. You build this fully connected neural network, and then you create your output. And if you look at the output, you have these gain, radiation, efficiency, bandwidth, resonant frequency shown along the vertical axis, and what is expected is shown on the horizontal axis, indicating that you're able to make very good predictions. Now, the benefit of creating a model like this is that you can now use this model to do all kinds of what-if analysis. It takes next to no time to do this. So that is why, trying to create this fast model, or what we call as a surrogate model, becomes very, very useful, because all of the information associated with that relationship is essentially buried in this kind of a model. So let's take another example. This is an example of a voltage controlled oscillator. And here the output voltage is a function of some frequency integrated over time, where this frequency is, let's say, another function of a control voltage. So you see the output voltage is related to one function here and a second function here, right? Where this frequency is basically the gradient of phase versus time. So I have a circuit that I'm showing over here with these control voltages as well as the output. So I can now create a neural network where this function G I can generate using this feed-forward neural network, what we call as a fully connected neural network. And the function F, I create another neural network for it. And then I have my inputs, I have my output, and then I compare it with what I would expect to be able to do my error control. And I can do the training using several algorithms that are readily available. This is an example where you can make use of a technique called backpropagation. Now, if you now make use of this fast model, you'll see that you can generate the results shown here as a behavioral model that sort of mimics exactly what a transistor level circuit model would do. So the blue represents the control voltage. And if you look at this waveform, the width of the pulse is continuously changing, indicating that the frequency is changing. And therefore, you can rely on this fast model to create all of these waveforms. The net result is that you save around 93% in terms of CPU time, because this becomes a fast model. Another nice advantage is that you are protecting the IP in the sense that you are not sharing the circuit itself with others. Now, question to ask is, what are we missing with these feed-forward neural networks? Now, if you're working with time series, basically time data, then there is this temporal dynamic behavior that you need to capture that you cannot capture with these feed-forward neural networks. And in general, when you have a high level of nonlinearity in circuits that have internal states or memory associated with it, it becomes very hard to capture that. And therefore, you need to somehow replace these feed-forward neural networks through another type of a neural network. So example of two kinds of waveforms that are shown over here. So the key message here is that the manner in which the switching occurs over here depends on what happens at previous time instance. Now, this is where a recurrent neural network becomes very, very important. And what you do in a recurrent neural network is that, let's say you want to create a mapping between the input and the output. You do that, but you also introduce this hidden state, where this hidden state depends on previous states that are shown over here. So you can create a neural network using not just the input and the output, but also these hidden states that become part of your neural network. So let's take an example. So this is an example of an I/O driver that we use to communicate between chips on a package. So I have a circuit representation of this I/O driver. And with any kind of a circuit, we are interested in relationship between current and voltage. And that is what is indicated over here. The difference is that if you look at this functional relationship, the current not only depends on the present voltage, but it also depends on the previous voltages at the output, the current at the output at previous time instances, as well as other voltages. We call these as supply voltages, both present and at previous time instance. So to capture this effect, we create this feedback loop that is shown over here. So you have a fully connected feed-forward neural network, but in addition to that, you bring this feedback loop to make sure that you're able to include your prior time instance as well. So you go through a learning process. And in this example, you're learning the relationship between the current and the voltage. And that is what is indicated here. So you have a bunch of voltages and currents, and you see you have this high level of non-linearity. You show this, you have spiking and things like that. That's what we call as the dynamic behavior. So you capture all of that, right, using a bunch of waveforms. So in this example, you use anywhere between 50,000 to 150,000 waveforms. You can automate the whole process, and the whole idea is to learn this nonlinear behavior. So once you have done that, right, you can now generate whatever output response you want, and you can also parameterize this whole model. So as an example, you can say that this transmission line should have a line width over a certain range, and all that information is captured in this machine learned model so that you can start generating eye diagrams and things like that. This example, we use something like 67,000 waveforms for training, but once you have trained it, to generate these kinds of waveforms gives you a tremendous speed up, right? And once again, you protect your IP. So next, let me get to frequency. Now, all of us understand the importance of frequency and a frequency response when we work with any kind of a package structure. So what we want to do over here is to predict the frequency response of any kind of a packaging structure. So how do you bring frequency into the neural network? One possibility is to bring frequency as an input, and I can create a fully connected neural network over here. The problem with this is it becomes very memory intensive. So as an example, if I have 500 design settings and each design setting has 2,000 frequency points, you multiply the two, there are 1 million data points that I have to learn. So another option is, why not include frequency at the output? So instead of at the input, you bring it at the output. Now, when you do this, the dimensionality of the problem becomes very high at the output, right? Question is, how do you train that? And is the question to ask yourself is this better since it is less memory intensive because you brought all the frequency points to the output? So as an example, those of you who work with scattering parameters or S parameters, if you're making use of 26 ports, with 2,400 frequency points, you're looking at 1.7 million outputs over here. The question is, how would you go about doing this? So I would like to focus on what is shown on the right-hand side today. So that brings us to another very interesting neural network called convolutional neural networks. And this convolutional network, neural networks are widely used in the computer vision community. And the idea here is that you try to mimic this human image perception. Now, what is the key takeaway with these convolutional neural networks? Now, if you look at these neural networks, right, for example, in the area of computer vision, one of the takeaways is that the nearby pixels and images are highly correlated. So therefore, you only need to focus on part of an image at any time. And that's what is indicated over here. So you make use of a filter as a way to be able to look at only parts of the image, and then you stitch these various parts together at the output. So as you go from the right side to the left side, the connectivity of these neural networks or these neurons becomes larger and larger, where you end up with a fully connected neural network over here and a very poorly connected neural network over here. So that allows you, both from a computational standpoint as well as from a memory standpoint. So that brings us to the frequency problem. So let us say that we take these CNNs or convolutional neural networks and we transpose it, right? So instead of having a fully connected neural network at the output, why not make it fully connected at the input, right? And loosely connected at the output. The reason why you can do that is because if you look at a frequency response, right, the data points next to each other tend to be highly correlated with each other, right? And the word spectral comes because we are looking at a frequency response. So if you look at this neural network over here, so you have some input parameters, you create a fully connected neural network to be able to create what we call as a latent space, which is defined over here. And all we do is we create this latent space and unflatten it to be able to get the frequency response for different kinds of design combinations. And then we pass this through these convolutional layers, what we call as 1D convolutional layers, that relies on the fact that frequency samples next to each other are highly correlated with each other. So we learned that, and then we are able to construct these different responses that are shown at the output. So let's see how this works. So let's take another example. This is an example of a solenoidal inductor for integrated voltage regulators. So you're constructing an inductor here, a solenoidal inductor, with different parameters associated with it. And one of the issues with all these inductors is that they tend to resonate. And when you work with a neural network, for example, a fully connected neural network, it is very hard to capture these resonances accurately. And therefore, you want to make use of something else. An example is this STCNN, or a spectrally transposed neural network. And by doing that, notice that the response that we are able to generate, basically the frequency response, is actually quite good, where all of the resonance behavior is captured very well. Now, oftentimes, when you create these neural networks with data, you want to create what we call as physically consistent neural networks. This means that even though you have data that you want to make sure that there are certain constraints you want to satisfy that is physics-based, right? And an example that I show over here are two kinds of physics-based constraints you want to satisfy. What we call as the causality, and the second is the passivity. Okay, so don't worry too much about what they mean, except that there is a model that basically tells you, if you want to satisfy causality, how the real and the imaginary part of a complex number need to be related to each other, and passivity relates to the singular values of the data that you're working with, right? So you can include these constraints into this convolutional neural network that I described earlier. So this was what I showed you earlier. You can add two more layers over here that satisfies this causality and passivity. But the key here is every time you satisfy this, you are incurring error in the data. And one of the nice things when you create a neural network is this error control. So you can train this neural network in such a way that not only can you satisfy these constraints, but you also minimize the error associated with satisfying these constraints. So let's take an example. So this is an example of a plated through hole in a package. And you see here, this particular problem has several parameters associated with it. So there are 13 input parameters. You're mapping it to 4-port scattering parameters. And you're trying to create this broad frequency response up to 100 gigahertz, lots of frequency points, 100 megahertz steps. So the output dimensionality in this case is around 12,000. And this is how you derive this number 12,000 that is shown over here. So let's look at the results, right? So you have lots of curves. So as you can see, we can generate data on the fly once you create this fast model. Now, if you look at this spectrally transposed convolutional neural network, if you look at this curve here, compare it with what the exact value needs to be, the error seems to be very, very small. However, if you take this frequency response and convert it into time response, you see this part here, the blue curve, which basically means that you're violating some physical constraints or a physics-based constraints. So you try to address that problem by adding these two extra layers that I showed you. And if you look at the frequency response, they look very, very similar to what I showed you earlier with this STCNN. But the difference is that when you convert this into time information, notice that the response turns out to be very, very good, and it does not, violate any of the physics-based constraints that are required, or phenomena that are required. And that same concept in terms of how you satisfy, or how do you make sure that the data or the model actually satisfies these kinds of physical constraints or physics-based constraints, is shown in these two graphs that are shown here. So let me go through the slide and then stop here, okay, and try to answer some questions. So what have we learned so far? We have understood the circuit behavior, the inputs and the outputs are known, right, over here, because I rely on a circuit to generate my output. So I always have data I can compare with in terms of what I get from the machine learned model and what the actual response needs to be. So we designed these neural network architectures that captured the behavior. These neural networks are expected to be always correct. We also call these as discrete neural networks. The meaning of this is when you make use of these machine learned model to make a prediction, you assume that that prediction is correct. But the question is, how do you actually know that? Because let's assume this output is unknown. How do you know that this prediction that you're making is indeed correct? So we have predicted the output in terms of the waveforms, frequency response parameters, and so on and so forth. So some of the questions you may want to ask is, what happens if the output response is unknown? Okay, so you have no output response, or you have very limited data. Number two, am I making blatant mistakes in my predictions? And number three, how do you establish a level of confidence in your predictions? So let me stop right here before I continue. And if there are any questions, I'll be very happy to answer. So let me try and look at the chat box.
It looks like we have 3 questions that were posted to the chat.
All right. Let me see. Oh, my cursor is becoming a problem. 1 second. Let me come out of this, if you don't mind. Okay, better now. Okay, the first question is there an intuitive reason for why feed-forward neural networks cannot capture resonance phenomena? The answer is it can, okay, except that you need to be able to create this feed-forward neural network in such a way that you have enough neurons in it and so on and so forth, very soon it becomes very, very memory intensive, number one. Number two, you have to realize that surrogate models by themselves have a limitation. I'll come to this later on. So depending on the dimensionality of the problem, these surrogate models will allow you to do these predictions only up to a certain point. And beyond that, you're not going to get any more useful information from these surrogate models. And when it comes to resonance behavior, you need lots and lots of points to be able to train a feed-forward neural network. It falls apart very quickly. The second question is, for modeling I/O circuits, what's the pros and cons of neural network versus IBIS model? Very good question. So when you look at an IBIS model, you are trying to capture the IV behavior, the current and the voltage behavior. And for that, you're making use of a table. And oftentimes, depending on how good that table is, you can introduce error into your response. However, the IBIS model protects the IP. The neural network model also protects the IP, but the difference is that the neural network model is derived directly from a circuit behavior. So whatever the circuit does, you are able to reproduce it almost exactly. So you don't rely on just these IV curves as a way to construct that model. So you can say that this IBIS model is a subset of a neural network model. So if you want to improve the model fidelity, then you probably want to move away from the IBIS model towards a neural network model. The next question is, approximately how many training samples are necessary to train a spectral transposed convolutional neural network, for instance, for 10 input parameters? My suggestion to you is please go and take a look at that paper because it has a lot of information in it. I've also provided another reference in terms of where this paper was published, and that provides all of the information you need for it. Next question is, how do you tackle process variation PV phenomena during using machine learning algorithms for prediction where when you don't have PV information, so you cannot train your network by applying PV information during training? Okay, so this is once again a very good question, process variations. So I'll try to discuss some aspects of it later on, but the whole idea here is once you're able to construct a good new machine learned model, that machine learned model can be used to be able to generate all of the process variations associated with it, including all of the corner points. I'll try to touch on some of that later on. So the next question is, how big are the typical models? Example, number of layers, parameters, etc. Now, if you look at packaging problems, in general, the number of layers you make use of and the number of parameters that you make use of is not even close to what the computer science community tends to use, or let's say the computer vision community tends to use. In general, the number of parameters we work with is anywhere between, let's say, 10 to 100 or so. And the number of layers, I would say, rarely goes beyond maybe around 20 or so, but it depends once again on the kinds of problems that you're trying to solve. Next question. When showing about predicting VCO voltage based on control voltage, there were two functions mentioned. Can both not be represented with one neural network? So this is where the domain knowledge comes in. If you look at the example of the VCO, First of all, a voltage controlled oscillator has no input. So the input really is, but it has a control voltage, right? That's number one. And number two is that if you look at the architecture that was created, the reason for using two neural networks is because you're trying to augment one with the other. So the first neural network allows you to calculate frequency, and the second network allows you to calculate the output voltage. So one can argue that the both can be combined with each other, but that's where the neural network architecture comes in, because if you read that paper, you'll realize that all we are trying to do is to take a fully connected neural network, augmenting it with another neural network so that we're able to separate out these two functions, and that provides some advantages. Okay, so last question I'm going to take, and then I'm going to continue. How to find proper settings for the neural network, like how many layers, neurons I should have, etc. Unfortunately, based on the information that I've provided you so far, there is no easy answer. So depending on the problem, you need to figure out how many layers you would need, how many neurons you need to use, what kind of neurons you want to use, how the connectivity needs to be, and so on and so forth. So that is where I think the domain expertise comes in. So there is no easy answer to this question. So with that, let me continue and maybe take the rest of the questions later on. Okay, Sherry, are you able to see my slides?
Yes, they look good.
So to answer some of the questions that I raised, let's go to the second part, which is on optimization. And I'm going to start with the design cycle here. And once again, this kind of a design cycle is not specific to just packaging. You can apply it on the semiconductor side and so on and so forth. Oftentimes, when you do design, you have a set of objectives and performance metrics. And then based on this, you figure out some design topologies, you explore the design space, create an initial design, and then you spend time tuning these parameters, and you come up with some kind of an optimal design. So the whole idea here is that if you look at this part, what is shown in the red box here, right? There are lots of iterations that one needs to go through to make sure that the design that you actually come up with indeed is the optimal design. And this is what we call as human in the loop. So the question to ask ourselves is there a possibility that we can completely eliminate the human in the loop by bringing in these machine learning techniques? So I'm going to focus on two elements to enable this. One is this automated design optimization, and the second is what we call as this uncertainty quantified model. So I'm going to start with a simple example. And once again, I'm going to focus on optimization first. So let us say that I have an input and an output. And I've constructed a total of 6 data samples that relates the input to the output. And I show you this graph and I ask you the question, where is the minimum given these data samples? And obviously the answer is, I don't know, right? So what we try to do is to fit a curve through these data points. So let's say I fit one curve through these data points, and based on this, I can figure out that the minima is right here. And that is what is shown over here. So the y-axis is the number of occurrences of the minima, and the x-axis is the position where the minima actually occurs. So there is one occurrence of the minima for this curve that is shown here. But the question you may ask is, how do you know that that is the right curve? that fits these samples to each other. So I add more curves. Let's say I create 5 curves that connects these 6 samples to each other. And based on each one of these curves, I determine where the minima is. And as you can see, some of them have single occurrences, some of them have double occurrences, right? The question you may ask is, how do you know that these 5 curves are sufficient? So I add more curves. And as you can see, as I add more and more curves, the frequency of occurrences of these minima, changes, and the position of the minima changes as well. So that is what we try to make use of. So let us say that we make use of infinite curves. So I have the same 6 data samples that I've connected together, but then based on these infinite curves, I have a spread in this blue line that is shown over here, right? So if I look at this, right, I call this blue line as my surrogate model. And I say that there is a certain uncertainty around these surrogate models shown by the spread that is shown over here. And I call these as confidence bounds. Now, the key thing to note over here is that I make the observation that these black samples that are shown over here comes from a simulator that is very computationally expensive. So I want to keep these black samples to a minimum as much as possible, and instead rely on the surrogate model as a way to do my optimization. Now, if you look at the second curve at the bottom, so the y-axis is your occurrences, and the x-axis represents the position. So this is nothing but your probability distribution function, right? So if you look at this now becomes a continuous curve. So it's no longer a histogram. And now based on the number of occurrences that I have, I can determine where the minima is going to be, right? And that becomes my next sampling point. So the next sampling point means that I'm going to make use of this expensive solver to add another sampling point over here so that I learn more about this function that is shown that connects all these samples to each other. And that is what is indicated over here. So you have a surrogate model, and in general, the surrogate model we make use of is called as a Gaussian process. Okay, it is a very well-known process or that has a certain mean and a covariance associated with it. And if you look at this this K over here, we call this as a kernel, and the kernel is nothing but a covariance function. Okay, and I'll explain to you shortly what this kernel actually represents. And if you look at this kernel, you'll come across some parameters you need to tune, and we call these as the hyperparameters. Okay, and hyperparameters are nothing but adjustable parameters that must be tuned to obtain a model with optimal performance. So if you look at this Gaussian process and try to plot it, this is what it's going to look like. So there's going to be a line that corresponds to the mean, and then there is going to be a spread over here that gives you your confidence bounds and so on and so forth. The second function that I showed you, which is the histogram that becomes a continuous curve, is what we call as an acquisition function. And we make use of this acquisition function to determine where the next sampling point needs to be. Once I've determined what the next sampling point is, I can make use of that to run my 3D solver to learn more about this system or this function that I actually have. So let's look at these kernels. So once again, there is a lot of literature, a lot of work that has been published in terms of the possibilities of the different kernels that one can use to be able to construct that covariance function, which is a measure of the variance that you're going to have in your response. Now let me try to pull out two of these, okay, and try to explain what these are. So this is an example of a squared exponential kernel. So what is the meaning of this? So I have two samples, xi and xj, and you see the relationship between these two samples are shown through this function over here. And that's why it's called as an exponential function. If these two samples are close to each other, that means that one is influencing the other quite a bit. The meaning of that is, if this number goes to 0, because they're close to each other, this value becomes 1. So a covariance of 1 means that the data points have high influence on each other. If they are far away, then this number will have a low influence on each other, right? And therefore, this covariance function is a measure as to how you're going to pick your samples, whether they are far away from each other or close to each other. Another example is this function called the Mettern 5-2 function. And you see this kernel, it's a lot more complicated. And if you look at this kernel itself, there are two parameters here, sigma f and lambda d. We call these as hyperparameters. Depending on the problem that you're working with, you need to tune these parameters to make sure that you're able to construct a good model that fits the data. Okay? And the links that are shown over here gives you a recipe as to how you can pick these kernels and so on and so forth. So each one of these kernels has a certain behavior associated with it. So depending on the kind of problem you're trying to solve, you determine which kernel to actually make use of. So that brings us to this Bayesian active learning and optimization. So how does it work? So let's say that you're looking at a 1D function. So you have one input and one output, which is shown as the function of the input, right? So based on this, I do a function evaluation, right? And then I rely on this model, right? Which is essentially my activation function to determine what the next sample needs to be. So which means that I'm making use of this 3D solver very few times and relying on my acquisition function to figure out where the next sample needs to be. We call this learning process as active learning because I haven't pre-constructed a model. As I add additional samples, I'm continuously learning from it. So this, I believe, is a must-have for packaging. And what this allows us to do is it takes this original problem, which is a very, very hard problem, where you're generating data from, let's say, a 3D EM simulator, and you're transforming it into a series of much easier problems to solve by making use of this acquisition function that is shown over here. So a few questions once again to ask yourself. How do you deciding the next sampling point? So you're relying on this acquisition function. You know that acquisition function itself has several peaks and valleys. So how do you know that that you're actually choosing the next sampling point based on the minima associated, let's say, with that acquisition function? So therefore, you have to do optimization. And the question to ask yourself is, if you're trying to do optimization of the acquisition function, and the acquisition function itself is highly non-convex, meaning that it has lots of peaks and valleys, then the optimization of that acquisition function itself can be very, very time consuming. The second is, how do you know which is the right acquisition function to choose? You just don't know because it is problem dependent. So you need some kind of a generalization capability. The third is, if I'm trying to cover a large design space, how do you actually make that happen? Because how do you try to address a large design space as well as reaching the global optimum at the same time? So let me put this in the context of another example or another problem. This is in the area of clock skew minimization for 3D ICs. Once again, the problem itself is not important, okay, because we're going to pose it as a black box problem. So if you look at this example here, I have a bunch of chips that are sitting on top of each other, connected through TSVs. The center chip has a clock distribution network. The top chip and the bottom chip have logic circuits. So as these circuits switch on the top and the bottom chip, it creates heat that generates a temperature gradient along the center chip. That temperature gradient creates clock skew. So your goal is to minimize the clock skew by trying to minimize the temperature gradient. And you do that by making use of a set of input parameters. So therefore, if you look at this problem here, this is represented as a black box where the input parameters you want to tune are shown over here. And you have the output, which let's say is the minimization of the clock skew. So this is an example with 5 control parameters. So let me take you through a technique called two-stage Bayesian optimization, and I'll show you how this works. So the way you do this is break up the problem into 2 parts. The first part is called fast exploration. Fast exploration means that you're trying to learn more about the system, okay? So therefore, you're looking at regions which has a large variance or uncertainty associated with the data, and you're creating sampling strategies around that. And then you do the pure exploitation. That means that you're trying to converge to the actual result. So therefore, you're looking at closely spaced points. Now, the method itself is broken up into 3 parts that are shown over here, right? And I'm just going to focus on one of the issues associated with learning acquisition functions, which was one of the questions that I raised earlier. I forgot to mention some of these techniques that I just mentioned, are available as open source at this link that is shown over here, the GitHub link. So if you're interested, please feel free to go and download this code and start playing with it. So let me address learning acquisition functions. So what you can do is that rather than working with a single acquisition function, work with a library of acquisition functions. So the examples that I shown over here is this upper confidence bound. I showed you earlier on what this upper confidence bound is. Similarly, you can look at another acquisition function, expected improvement acquisition function, for example, EI. So you have a library of acquisition functions. And as you go through the optimization process, you learn which acquisition function is appropriate depending on what stage of the solution you're looking at. And that is what is indicated here. So not only do you learn the behavior of the response or the function, but you also learn the acquisition functions. There is a way by which this can be done. So let us see how this works. So if you look at this response surface here, it's a 2-dimensional problem. So I have two inputs, x1 and x2, and let's say 1 output. Now, this triangle represents a sample that I've created, let us say using my EM solver. And this represents iteration number 1. That's my starting point. So I have 1 data point. Now I use a sampling strategy to create these circles, what we call as candidate points. And making use of these candidate points, I make use of the acquisition function to figure out where exactly the next sample needs to be. So in this example, the next sample should be at x1 equal to -1 and x2 equals to -1. So I take this and run my 3D solver to generate another data sample, which would be a second triangle. Notice that in this response surface, the global optima is right here, shown as the diamond. As I go through this process, let's say I go to iteration number 15, you see you're going to have a lot more triangles. That means that I have run this 3D solver to learn more about the system. This is the exploration stage, right? And based on this, right, I also create these circles, which represents my candidate points based on my sampling strategy at iteration number 15. And based on this, I determine that the next sampling point needs to be over here, corresponding to x1 equal to 1.5 and x2 is equal to 0.5. I run my 3D solver again. When you go to iteration number 42, notice that slowly, if you look at these triangles coming from the 3D solver, you're slowly beginning to get into the space that contains this global optimum. So this is what we call as the exploration part, and at iteration number 42, you complete the exploration part of the problem. Then you get into the exploitation. So here you're trying to converge to the exact answer. So you're looking at data samples right next to each other, right? And so you reach this global optimum, which is shown as the diamond here. So let us see how these results look like, right? So I take the same example, and what you see is the blue curve over here represents the convergence of this method that I just described. So the x-axis represents the number of simulations you're trying to make use of. Y-axis represents your clock skew. So the first part, which is the steep part over here, represents your exploration. So very quickly, you try to come to the region that has the global optimum. Then after that, you try to converge to the exact value. So this part over here depends on the kind of accuracy that you're looking for, right? Now, we've also compared this with two other methods. One is what we call as a nonlinear solver, shown as a green curve. And IMGPO is another machine learning based algorithm that has been used in the neuroengineering community. So if you look at the convergence for both of these techniques, it's not as good as what is shown over what I just described. Now, the takeaway from this is that oftentimes people say that you can make use of a machine learning technique that is available, what we call as a toolbox, and blindly apply it to your problem. The answer is no, because if you do that, you'll only get so much of a benefit. You need to understand the data structures. That is where the domain expertise comes in. And once you understand the data structures and the samples that you have, then you can come up with a much better solution as compared to what is out there. So in this example, you get roughly a 4x speed up in terms of the convergence compared to this IMGPO, which is a readily available Bayesian optimization based solver that was developed, as I mentioned earlier, in the neuroengineering community. So let us take this method that I just described and say what happens if I want to increase the dimensionality from 5 to something much higher. And you will find that very quickly you will start meeting two fundamental problems. The first one is what we call as the statistical problem. How do you construct a high dimensional predictive model with scarce data, especially when parameters interact with each other? Okay. Now this is where the kernel comes in, what we call as the surrogate model. The surrogate model, right, is only as good as the kind of model that you're making use of, or the kind of kernel you're making use of to construct that model. So if that model is not good to begin with, you'll always hit a wall in terms of how much additional information you can get from that surrogate model. The second is algorithmic. How do you choose the next sampling point? Because if you do this auxiliary optimization that I mentioned earlier, right, it is not very practical. As you start increasing the number of parameters, let's say from 5, if you go to 30, you have a very complex surface for the acquisition function to begin with, and you're doing optimization on that surface that can take a lot of time as well. Let me try to address both of these issues very briefly on the next slide. So if you want to scale this optimization technique that I just mentioned to higher dimensionality, you can change the kernel. So what you do is you can construct what we call as an additive Gaussian process. And the idea here is that you try to create different kernels that you can basically start adding to each other. And depending on the kernel that you're making use of, you capture either the first order interactions, the second order interactions, or even the dth order interaction. So this additive Gaussian process is a superset of the conventional Gaussian process that I just mentioned earlier. The second issue is, how do you go around this whole optimization problem, what we call as the auxiliary optimization on the acquisition function? And the answer to that is, you have to create some kind of a tree structure where you rely on candidate points, and based on these candidate points, you develop some kind of a method that allows you to figure out which one of these candidate points you can actually make use of as your next sampling point. So once again, this method is available for you to download from this link that is shown over here. So let us see how this works. So I'm going to take the example of an RF wireless power transfer system. And in this example, right, you have a very complex circuit, right, where some of the circuit elements are in the form of a layout and others are in the form of transistors. And the goal over here is, since it's an RF wireless power transfer system, the input is RF power, the output is DC power. So your goal is to maximize the RF to DC harvesting efficiency, while at the same time minimizing this RX coil area so that you can build a miniaturized system. Okay? So this example has a total of 32 parameters. Remember, from 5, we have increased it to 32. And so let us see how this works. So the results are shown over here. So if you look at this method, so this is the additive Gaussian process along with this deep partitioning tree, where the system efficiency you're able to reach is around 60% or so, right? With a coil area of around 11%. And if you compare it with some of the evolutionary algorithms that are out there, for example, particle swarm, you see the efficiency is lower, but the coil area is smaller as well. Now, there is a way by which you can control or weight which one of these parameters is more important to you. So in this example, it was weighted in such a way that this system efficiency had a higher weight compared to the RX coil area. Now, what you see in the center is a run-of-the-mill, or what is readily available as an additive Gaussian process code. And if you blindly make use of that, you see that even though the system efficiency comes close to what was shown, the RX coil area becomes very large. So once again, the takeaway here is that you get quite a bit, you gain quite a bit if you are able to understand the problem and make changes to the neural network based on that information. Now, if you look at these two boards, the first one was hand-tuned, took us around 6 months. The second one is this machine learning-based solution. You see, you get an advantage not only in terms of performance, but in terms of size as well. So with that, let me move on to the last part of this presentation before I get into future directions. And this is in the area of creating uncertainty quantified models. Very important. When we looked at optimization, our goal was just to reach the optimum, right? But why not generate a model at the same time while we are reaching the model? While we are reaching the optimum. That's what we call as model building. So the idea here is that instead of just sampling to be able to reach the optimum, why not sample wherever the variances are very large so that you can also construct an accurate model at the same time? So that is the concept that is shown over here. So once again, this is available for free download from this website. So the question is, what is the importance of this uncertainty quantification and what exactly does it mean? So let me not focus too much on these equations over here. So let us see what we have done so far. When you do training for optimization, right? Remember the variances that you're generating basically quantifies the uncertainty around the data, right? So if you have lots of samples, the variance gets reduced, therefore you reduce the uncertainty around your predictions. Now, another issue still remains, the hyperparameter. So how do you know that if you set the value for that hyperparameter at a certain value X, that the same value X can be used when you're trying to work with another set of data? So this hyperparameter value constantly needs to be tuned so that you're able to fix the model. That becomes an uncertainty. There's a way by which you can include that uncertainty in your model generation as well, and that is what is indicated over here. So using this second approach that is shown over here, not only do you account for the data uncertainty or the uncertainty associated with the lack of data, but you also include the uncertainty associated with the quality of the model as you tune these hyperparameters. So let me show you a last example, okay? And this is in the area of high-speed channel signaling. So I have two chips here that are sitting on a package, and they're communicating with each other through this board. And so the idea here is to be able to do differential signaling at a very, very fast data rate from the transmit side to the receive side. And there are several parameters that you need to tune to make sure that this communication is possible. So if you look at the parameters that are shown over here, and if you look at the combination of these parameters in the discrete sample space, it's around 1125 combinations. So if you try to do it one at a time, as one would expect, it takes a huge amount of time to simulate. And the goal over here is not only to include this kind of a design space, but let's say that we want to look at process variations, and we also want to look at the corner points, right, where things could potentially fail. So let's look at the results, right, once you apply this technique that I just showed you earlier. Now, what we are showing here is a parameter associated with the eye diagram that you're creating for the channel. It is the horizontal eye opening shown as a percentage. The blue curve represents the actual value. So you're actually running this fairly complex simulator to create these blue data points that are shown with a curve joining all of them. So that is the actual value. Now, based on this model that we have generated, we create these orange or brown dots, right? So you see that around each one of these brown dots, there is a shaded area associated with it. We call this as the confidence bound. So that captures the uncertainty around the lack of data, as well as the uncertainty associated with tuning the hyperparameter. So the key takeaway over here is that if you look at this blue dot, right, and this brown dot that is shown over here, within the range that is shown here as the confidence bound, we are able to make very good predictions. So not only do we give you a number, we also tell you what is the range around that number, which is the quantification of the uncertainty around that. So let us say that based on this, you want to improve the confidence bound. So you want to reduce the shaded spread that is shown over here. If that uncertainty is coming from the lack of data, all you need to do is to add more data samples to this. And the way you add more data samples to this is to run this technique that I showed earlier as active learning for a few more iterations so that it's able to gather more data so that you can reduce the error around your predictions. So with that, given the 5 minutes that I have, I'm just going to conclude by taking you through 3 topics that I believe are very, very important for this community. The first is in the area of scaling. So far, everything that I showed you takes you up to around 50 dimensions or so. So let's say you have input parameters, 50 of them, you have this very complex response surface. You either want to generate a model or you want to do optimization around it. It's doable. Now, one of the challenges that we face is every time we create a surrogate model, right, as the dimensionality increases, as I mentioned earlier, you no longer get any more useful information from it. It is like a bucket, right? As you fill the bucket with water, once it's full, the bucket is not going to be a whole lot useful anymore. And in fact, sometimes, right, it can actually work against you. So the same concept works over here. So the question is, how do you start increasing the dimensionality? And this is where the domain expertise comes in. So most of these machine learned models that I showed you, there is a way by which you can list the sensitivity of these parameters almost for free. And one example is shown over here for the wireless power transfer example. Okay, remember it had 32 parameters or 30 parameters, and each one of these histograms represents one input parameter and the sensitivity associated with that, which is the height of each one of these histograms that is shown over here. So based on this, clearly, not all parameters have the same level of sensitivity. You can make use of that information to reduce the dimensionality of the problem. One way to do that is a method that we call as PLS or partial least squares regression, where in that example that I showed you, you can reduce from 30 parameters down to maybe 3 parameters. We call these as 3 principal components and do all your optimization, let's say, around that. So if you're interested in something like this, you can certainly take a look at this paper, but this is just some ideas of how one can do this, not the only way to do this. The second is what we call as extrapolation. And you can do this for frequency, you can do this for design space. And the concept is the following. All of the examples that I showed you had a certain design space associated with it. Let's say in this example, it's a frequency range up to 12 gigahertz, and the vertical axis is, let's say, the impedance. So all of your training occurs in this space. Let us say that you want to go outside of the space, for example, beyond 12 gigahertz. The only way for you to make predictions is that you need to relearn what happens in this region. However, there is a way by which you can take these neural networks, create an architecture in such a way that you can try and generalize the solution, whereby once you have trained it over a certain space, you can use the same neural network to extrapolate outside of the space. That's why we call this as extrapolation. One example of a neural network is shown over here. This is not the only way to do it. There are other techniques as well. The third is what we call as invertible neural networks. It's not an easy neural network to generate, but the benefits from it can be huge. So far, all of the neural networks that I described to you works in the forward direction. Given an input, you map the input to the output so that by making use of the neural network, you make your predictions. Let's say you want to do the reverse. So given an output, I want to predict what the input parameters need to be. So think of a scenario where you have a very complex problem. For example, the antenna problem that I described as problem number 1, where you're interested in the gain of the antenna. And based on that, you want to figure out what should be the size of your particles, the metal particles. So the inverse process requires one to think a little bit differently in terms of how you would create these neural networks. We call these as invertible neural networks. And there are ways to do that by making use of these distributions that are shown over here. This is an example applied to a substrate integrated waveguide at very, very high frequency, where we were trying to figure out if there are ways by which you can predict what these dimensions need to be based on the response we were interested in. Once again, what is shown over here is just one way to do it, not the only way. So with that, let me summarize by saying that I covered a little bit of work in the area of neural network development and design optimization. This uncertainty quantified models, I believe, is very, very important to all of us, because without including this, a lot of the predictions that you make may or may not be accurate. And there is some way by which you can quantify that. And in terms of future directions and opportunities, I listed 3 examples over here. And as I mentioned earlier on, if you're interested in downloading some of this code, feel free to go to this link and download them. So with that, I would like to stop here. Thank you very much for joining us today. I've shown some photographs of some of my students, postdocs, research engineers, and so on and so forth, that are working on these kinds of problems today, as well as worked with me before. And if you have any questions, please feel free to send an email to this email ID shown over here. And also, I would encourage you to go to our website, prc.gautech.edu, and take a look at what we do. Thank you very much for joining. And what I'll do is stop now and try to answer some of your questions. Thank you so much.
Dr. Swami, may I share the questions from before?
Yeah, I'm going through the chat box. Okay.
The ones in blue were from the first part of the session that were not yet answered.
In the interest of time, let me try to go to the second part of the session. So let me touch on what courses would you recommend to a student interested in this technique. There are so many online courses that are available, that covers the basics of neural networks, Bayesian optimization technique. In fact, if you Google these kinds of topics, there are lots of tutorials that are available, both in terms of videos as well as published documents. So I would highly recommend that you do that and try to read through them. The concepts, some of them, though they may look to be very overwhelming, once you understand these concepts, trying to convert them into a piece of code actually is quite easy, because a lot of them you can make use of built-in functions, either in MATLAB or Python, to be able to enable these kinds of algorithms. The second question is, how are the candidate points actually determined in the progression of TSVO, and approximately how many candidate points are required to predict the next sample accurately? All right, so the candidate points comes from the sampling strategy that you're actually trying to make use of. So I mentioned initially this Latin hypercube sampling strategy. So that is one way by which you can figure out what these sampling points are, right? But if you look at the literature today, there are other kinds of sampling strategies that are available which can work for specific types of problems. So what I described to you is one example of a sampling strategy. We call this as the deep partitioning tree. And all you're trying to do here is to take the space that you're trying to work with, break it up into tiny volumes, and sampling from each one of these volumes and making some assessments based on that. The third is confidence bound derived from infinity curve fitting? If so, then how to get those infinity curves? Yes, so uncertainty, as I mentioned earlier, okay, comes from two sources. One is the data or the lack of data, and the second one is based on the hyperparameters that you're tuning in your model, right? So if you look at this infinite curve fitting that I mentioned, that corresponds to the data. So when you make use of this Gaussian process that I mentioned earlier, automatically those confidence bounds come into play, okay? But as you start bringing in the uncertainty associated with your parameters and things like that, the hyperparameters, it gets a little bit more complicated. All right, let me see if there are any other questions. I think that was it, right, Sherry?
Yes, I believe so.
Very good. Thank you so much. It is noontime here in Atlanta. Thank you so much for joining. And as I mentioned earlier, any questions at all, feel free to send me an email. And do go to our website, take a look at what we do. Thank you so much for joining. Take care.